In this question, we are required in part A to find the fifth degree Taylor polynomial centered at x is equals to 1. So I'll just start with part A. What that means is you're going to find derivatives of f of x and plug in 1 to find the Taylor series expansion for this function. Okay? All right, so let's get started. So f of x is equals to ln x, and the value of this function at x is equals to 0 will just be at x is equals to 1, sorry, will be equal to ln 1, which is just 0. Okay, remember, why am I doing that? Because it's centered at x is equals to 1. Okay, the first derivative of this function will be 1 over x. So the value of the first derivative at 1 will just be 1. The second derivative of this function will be negative 1 over x squared. So the value of the second derivative at x is equals to 1 will just be negative 1. The third derivative of this function will be 2 over x cubed, and the value of the third derivative at x is equals to 1 will be equal to 2. The fourth derivative of this function will be equal to negative 6 over x to the power 4. The value of the fourth derivative of this function at x is equals to 1 will be negative 6. All right. Now these guys have asked us to go up to the fifth degree tailored polynomial, so we have to keep on going. Fifth derivative of this function will be 24 over x to the power 5. So the value of the fifth derivative at x is equals to 1 will be equal to 24. All right. So what we need to do now is to plug these coefficients into the formula for Taylor series. Which is here. So we need to plug it into the formula for Taylor series. This one here. All right. So what I'm going to do is, remember here, our A is 1. Okay. So I'll just write these expansions here. So f of x will be equal to f1, all right, because A is 1, plus x minus 1 f dash 1 plus x minus 2 over 2 factorial. This is all from here. Okay, I'm not creating them. Sorry, this is x minus 1. Squared over 2 factorial, and this is f second derivative at x is equals to 1 plus x minus 3. The part, why do I keep on writing that? So x minus 1 to power 3 over 3 factorial f3 1 plus x minus 1 to power 4 over 4 factorial f4 1. Let me just write this f3, that derivative, plus x minus 1 to power 5 over 5 factorial multiplied by the fifth derivative. And this goes on to infinity. So now we need to plug in the coefficients that we have here. All right. So if we plug in these coefficients, what we'll end up with is x minus 1. F1 is 0, right? So F1 is 0 here. So that's gone. And then the value of the first derivative at 1 is 1, which means we end up with this guy here, x minus 1. We're actually starting from there, minus x minus 1 squared over 2 factorial plus 2 x minus 1 cubed over 3 factorial. Right, again, where did that get 2 from? Here. Okay, and let's carry on. Minus 3 factorial x minus 1 to power 4 over 4 factorial. And then remember, this is same as negative 3 factorial, and this is 4 factorial. I think I mentioned that previously. Especially if you have factorials in the denominator, it's easier to write the numerators as factorials. It doesn't change anything. It's a calculator paper anyway. So we carry on, and then what you have next will be plus 4 factorial x minus 1 to power 5 over 5 factorial. Okay. And then we have to simplify this. So this will be equal to this one and this one will simplify. That and that will simplify. That and that will simplify. So what we'll end up with here will be 3. Here we'll have 4, and here we'll have 5. So we'll end up with x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to power 4 over 4 plus x minus 1 to power 5. Okay. So it's good to go back and check again that everything makes sense. All right. So we now have, remember the question was, find the fifth degree Taylor polynomial centered at x is equals to 1. I think that's all. That's what it is. Now, the second part, so that's done. The second part, use this polynomial to approximate ln 1.3, right? So ln 1.3, what that means is you are going to plug, so here, just plug 1.3 in place of x. All right. So we're just going to plug 1.3 in place of x in this expansion. So what we have is ln 1.3. Okay, I need more space here. So ln 1.3 will be 1.3 minus 1. So that will just be 0.3 minus 0.3 squared over 2 plus 0.3 cubed over 3 minus 0.3 to power 4 over 4 factorial plus 0.3 to power 5. So not 4 factorial. Already on autopilot. So 0.3 minus 0.3 squared over 2 plus 0.3 cubed over 3 minus 0.3 to power 4 over 4 plus 0.3 to power 5 over 5. Now, so that is our expansion. We are trying to use our expansion to find the value of ln 1.3. So you can just plug that in your calculator, and that will be 0.262461. All right. All right, let's carry on. So part C, so you're done with part B. Use the Lagrange error term to determine the upper bound to the error in this approximation. So what will be the error at most in this approximation? So first of all, we need to find the magnitude of error. Now we know that the error term is given by this formula, and I'll use the one that I have in my videos. The one that you have in your formula booklet, it's similar, but just with different letters. So as long as you know what you're doing, you should be able to use it correctly. Okay, now just remember here, x is equals to 1.3 because that's what you're using up, the x value that we used in approximating ln 1.3. C is equals to 1 because the polynomial is centered at x is equals to 1. N is equals to 5 because we use the fifth degree polynomial. Okay. So we can plug these guys into this formula and see how the formula looks like before we carry on. So which means R5x, now x is 1.3, will be equal to the nth plus 1 derivative of f at z. Now n is 5, so that will be the sixth. So that will be the sixth derivative at z. and then c is 1, so x minus 1 to the power 6 over 6 factorial. Now this, remember, this is the magnitude of error. Okay, that is the magnitude of error. So, so what we have to do is we have to find this bit. We have to find what this bit is. All right. Now, let's go back to our solution. Up, up, up. So fifth derivative was that. So fifth derivative was that, which means that sixth derivative sixth derivative will be equal to negative 120 over x to the power 6. All right. So that means that the sixth derivative will be equal to that. So what you are going to do is we can find the value of the sixth derivative at z. That will just be negative 120 over z to the power 6. So which means our formula will be okay, up there. So r 1.3 will be equal to the absolute value of negative 120 over z to the power 6 multiplied by x minus 1 to the power 6 over 6 factorial. Okay. Now, there's another thing that we need to think about. Okay. Since z is between 1 and 1.3, by inspection, there will be a larger error if z is equals to 1. Because if you now let me just write this statement here. Since z is between 1 and 1.3, what I'm saying here is by inspection, there will be a larger error if z is equals to 1. So there will be a larger error if z is equals to 1. Now, why? Because z is between, oops, I need a highlighter. Z is between 1 and 1. So you can pick any value of z between 1 and 1.1 and 1.3. I already mentioned why, all right, when I mentioned about this formula. We pick z, all right? So z is between x and c, all right? X is 1.3, c is 1. So suppose you plugged in something like 1.3. Whatever you'll end up with here will be, and by the way, this one here is, this will actually be, this will be 1.3 minus 1, which will be 0.3. But anyway, what I'm trying to say here is, in fact, let me change that before. So that will be 0.3 to the power 6. So what I'm trying to say is, if you picked, for example, you're dividing by z to the power 6. If you picked something like 1.3, the value that you end up with, the magnitude that you'll end up with, will be smaller. If you picked something like 1, you're dividing by 1, all right, the magnitude of error that you end up with will be larger, all right? And what I'm trying to do here is we are trying to use this error term to determine an upper bound to the error in this approximation, the upper bound, all right, the maximum error. What's the magnitude of the maximum error? So we are going to use z is equals to 1, which means that the magnitude of error in this case will be negative 120 over 1, or just negative 120, multiplied by 0.3 to power 6 over 6 factorial. All right, and if you work out the value of that, what you'll end up with is 0.0001215. Okay, so that's what you'll end up with. So which means the error is at most this value. All right. So let's carry on. We're done with that question. So that was part B. All right. So now we are moving on to part D. How many terms of the Taylor series centered at c is equals to 1 are needed to approximate ln 1.3 so that the error is less than 0. All right, good. So how many terms? They want us to find n, right? The Taylor series centered at c is equals to 1 are needed to approximate that. Okay, so which means our c is 1 and our x is 1.3. So we will start by writing the error term, just creating space here. So this is part D. So part D, the error term at 1.3 will be given by, so this is the magnitude of error, the nth plus 1th derivative of f at z multiplied by 0.3 to power n plus 1. Remember, we don't know what n is. That's what you're trying to find. Okay. So we can carry on and try to find what we need. So we need the nth plus 1th derivative. All right. So we need to find the all right.